Hello, hello Karthik. Please let me know if I'm audible to you. Am I audible? Okay. So good evening, and how are you doing today, Karthik? And how was your day? Was it good? Okay, very nice. So let me introduce myself. I'm Prabhas Singh, and I'm the mentor of today's session. I hope you are excited to learn something new in physics. Are you excited? Okay. So, before we begin, let me ask you a question. Have you ever looked into a swimming pool or a pond and noticed that the fish or the bottom of the pond appears little closer to the surface than it is actually? Have you ever noticed? Okay. So, it's strange now. Okay. So, we are going to understand this mystery in this session. And what happens inside the fluid, or inside the pond, why fish appears little closer to the surface. Okay, so first of all, let us suppose this is the pond, this is the pool, and this one is the fish situated inside the pool. And let me show some parameter over here. Let us suppose this is the depth of the pool, this one is the depth. The fish is just like an object. Okay, so the depth of the fish from this interface, this is known as interface. Interface means boundary which separates two medium. This medium is, this one is water and this one is air. Okay, let us suppose the refractive index of water is mu d. D stands for denser medium, because we know that water is denser compared to the air, and refractive index of the air is mu r. Mu r is the refractive index of the air. R stands for rarer medium, because air is the rarer than water. Okay, and the depth of the object from this interface, we are going to measure all the parameters from this interface. And depth of this object, it means fish, depth of the fish from this interface is do. Okay, and an observer stands outside the pond, and we have to form the image of the fish. So first we have to draw some incident rays on this interface. So this one is let me represent this fish with a point. Let us suppose this one is the fish. Okay, this is our first ray which incident on this interface, and this one is our second ray which incident on this interface. And as we know that the rays, both the rays, either this one or this one, both the rays are going from denser to rarer medium. It means both the rays are going from water to air. So first of all, we have to draw normal at the point of incident. So this one is the first normal at this point, and let us suppose this light ray incident normally to this interface. It means this one is 90 degree. And as you know that denser medium to rarer medium, it bend away from the normal. It means what will happen here? The light will go like this. Okay, this one is our refracted ray. This one is our refracted ray. This one is our first refracted ray. And what about the second refracted ray? So when a light incident normally on any surface, then it has no deviation. It has got no deviation. It will pass like this without any deviation. So this one is our second refracted ray. This one is our second refracted ray. And you know the point of intersection of refracted ray will be the image. So you can see here that the both refracted rays are diverging in nature. They are not going to meet anywhere in the air. It means what should we do now? We retrace the path of the refracted rays in backward direction. So let me first retrace the path of light rays, these refracted light rays. So this one is the first and this one is the second, and you can see clearly that both the light rays intersect at this point. It means you can see that this is the point of intersection of two refracted light rays. This is the point of intersection of two refracted rays. The first one is this and the second one is this. And you know that the point of intersection of refracted rays is known as image. It means the image of this phase, which was considered as the object, the image of this phase will be over here. Okay, so simply you can see that this will be the image of the fish, and light actually meeting over here. It means this is virtual image of the fish. This will be the virtual image of the fish. And let us suppose the depth of this image from this interface, and let us suppose this one is the depth of the image. Image, it means the image of the fish. Let us suppose this is di, depth of image. What about the angle of incident? This one is the incident ray, so this is considered as angle of incident, I. This is our angle of refraction, R. Okay, if this angle will be I, then this is also equals to I, because these both are alternate angles, alternate interior angles, both will be equal. If this angle is R, then this is vertically opposite angle, this is also be equals to R. If this one is R, it will be equals to R. Okay, and let us suppose this distance, let us suppose this one is X, and let us suppose this point you can name let us suppose this one is P and this point is Q, this is O, and this point is, let us suppose, I. So first we are going to derive a relationship between virtual depth. This depth is known as virtual depth because this is not the actual depth of the fish. This one is the actual depth of the fish. This one is the actual position of the fish. It means what is the actual depth of the fish? DO. This one is the actual depth of the fish. DI stands for distance of or depth of image from this interface, or it can be also called the virtual depth of this object. Okay, now we're going to derive a relation using Snell's law at that point, at point P. So at point P, let me change the color of the pen. So at point P, using Snell's law. What about Snell's law? Snell's law, mu1 sine of theta 1 is equals to mu2 sine of theta 2. Theta 1 is the angle where the theta 1 is the angle between incident ray and normal in the medium where the object is placed, and mu1 is the refractive index of the medium where the object is placed. So object is placed in the medium, so this will be equals to mu1 and this will be equals to mu2. So at the place of mu1 we use mu d, sine of theta 1. Theta 1 means this angle, the angle of incident in the first medium. This one is considered as a first medium, this one will be considered at the second medium. So at the place of theta 1 we use angle of incident I. Sine I is equals to mu2. Mu2 means where the light goes after refraction, light goes in air, so mu2 will be equals to mu r. So mu r sine of, at the place of theta 2 we use the angle of refraction in the second medium, this is equals to theta 2, angle r. Okay, as we know that in ray optics all the angles are very very small, chunki angle I and angle R are very very small. small. In this situation, sine theta can be written as theta, or it can also be written as tan of theta. It means you can use tan I at the place of sine I. So mu d tan I is equals to mu r tan of r. What will be tan I? So look at the triangle OQP. So in triangle OQP, tan I, this is a right angle triangle at point Q. So we can calculate the value of tan I from this triangle. Tan I will be equals to perpendicular yani QP divided by base QO. QP is equals to x and QO is equals to depth of object total DO. Okay, what about tan R? Tan R is equals to, you can simply calculate the value of tan R from this triangle IQP. Tan R will be equals to x divided by this distance. So this will be equals to x. So x divided by this distance is equals to di. Put the value of tan I and tan R in this expression. So this is mu d tan I is equals to x divided by do is equals to mu r, and tan r is equals to x by di. X got cancelled out. So we have to calculate the value of di. Di will be equals to do mu r mu d. So di will be equals to do divided by mu d divided by mu r. Mu r. Let me write it at another place. I'm sorry. Let me erase it and write somewhere else. So finally we have got, let me change the page. Di is equals to do divided by mu d divided by mu r. So we can see an example over here. Let us suppose this one is the interface, this one is the fish, this is the water of refractive index, and refractive index of water yani mu is to 4/3. This is air, refractive index of air will be equals to 1. And let us suppose the fish is situated at a depth of 16 meters from this interface. It means 16 meter, this is depth of the object, and we have to calculate the value of virtual depth, or we have to calculate the depth of the image of the fish. So put all this parameter in this formula. So di will be equals to do depth of object, which is 16 upon mu d 4/3 by mu r. Mu r is equals to 1. So this will be equals to 16 multiplied by 3 divided by 4. 4 4s are 16, 4 3s are 12. It means the image of the fish, image of this fish appears over here, and this depth will be equals to 12 meter, and we have already calculated it. So that's why object inside the water appears somewhat closer to the surface. Not this is not about the fish or frogs, this is about all the object situated in the liquid or water. So this is the mathematical calculation about this mystery. Okay, so Karthik, first of all, so that was our discussion on why the fish is in the pond or the bottom of the pool appears to be uplifted, and how we deliver the relationship between real depth and apparent depth. I hope you enjoyed learning the concepts as much as I enjoyed teaching it to you. And before we wrap up, can you tell me honestly, can I ask you something? Hello, Karthik. Okay. How did you find this session? On a scale of 1 to 5, with 5 being what rating would you give today's demo class? Okay, it's fine. Thank you so much. Your feedback really helps me to make my session even better. I'm excited to continue exploring more interesting concept with you in the upcoming session. Thank you. Have a good time.